Okay, the aim today, guys, is to have a look at Section 9 and Section 10 of our electromagnetism booklet. We want to look at part of Section 10 first, just to put Section 9 in context. So if we start off, and what it says sort of up the top here is really true. It's changing, thankfully, but most of our mains electrical energy is still generated in massive generators sited in power stations and therefore is then sent across the state through overhead cables. So a good example here in Perth, Mugis power station is down near Collie because that's where the coal is. Right? That's where that fossil fuel is located. So that's where the the electricity is generated, and the majority of electricity for Perth is generated there, and it's about 200 k's away. It's easier to transmit that electricity through large transmission lines than it is to truck the coal closer to Perth and then burn it, creating electricity close to the supply. So that's all well and good. The trouble is, though, is that whenever you transmit or conduct electricity through a conductor, as shown by these thermal images, you've always got some form of energy wasted as heat. Okay? So, as you can see there, the brighter the image, the more heat that's generated. Okay? So it doesn't matter how efficient the material, the thing is, the transmission is, you're still going to get some heat. So one key principle, the first key principle, is that you want to minimize that heat loss from your conductors. How do you do that? That's the key. All right. We're going to go to the formulas that we looked at last year. And like it says here, the aim is, and we'll highlight that, the aim is to minimize the heat loss from the grid system by having as low a current as possible flowing. Okay? It's about minimizing the current in those transmission lines. Why? Because of these formulas here. So we look at P lost. Power lost is due to power loss because of heating. The key formula for this is I squared R. Electrical engineers and Sparkies call them I squared R losses. The thing to remember is that the amount of power you lose as heat is not proportional to the current. It's proportional to the square of the current. So what you've got to do is you must minimize it because it's proportional to the square of the current. If we double the current, we quadruple our heat loss. 10 times the current is 100 times the heat loss. So that's a really critical factor. Okay? So if we look at task 11, that guides us through this a little more. It says, use the formula above to complete the following. Assume the power output, P, remains constant. And we'll talk about that in a minute. But every 10-fold increase in V, your voltage, means a 10-fold decrease, in your current, and therefore a 100-fold decrease in your power loss. And so from P is equal to V times I, in order to have a small current, your voltage that you transmit the electricity at must be large or maximized or as big as possible, So as it says in our notes, hence the output voltage from a power station is usually stepped up from up to 330 or even 500 1,000 volts, like joules per coulomb. It's transmitted, in the case of Muja, to Perth, a couple of 100 kilometres, and then it's stepped down again to where it's needed. Okay? So if we flick to the next page, that gives us a bit of a little bit of a schematic diagram. Yeah. So this one is not in your notes, but there's a very similar one in your notes as well. Okay. Which would be on page 44. So if I skip to page 44, got to go back. There we go. There's page 44 there. So here's the key, yeah? You got your power plant on your left-hand side. In our case, it's down near Bunbury. Between sort of here and here, you have several hundred kilometres. Sometimes it's greater. So you got a large distance D there. And if you transmit through those wires a large current, those wires are simply going to get hot and you're going to lose energy. So if we compared the amount of energy output, say, at the start of your distribution, it's going to be much more than what you actually receive at the other end. Because across that distance, you're losing energy in the form of heat. Okay? So, and that's why we want to minimize the current. So we want to minimize these I squared R losses. How do we do that? High voltage. Okay? That's essentially section 10 in a nutshell. We'll come back and do that more. But what that does is give us a context for section 9. Section 9 is, okay, how then do we step up our voltage? How do we step up our electricity to 40, 50,000 volts? And that's the idea of a transformer. So, go back in your notes now. We want to go back to, what are we looking? We're looking at page 39. So I'll pause there and then go to page 39. Alrighty, so here we are, section 9, page 39 of our notes. We want to look at how current can be stepped up and down, and that's the job of these transformers. So we'll look at these dot points to start with, and essentially a transformer is something that increases or decreases the voltage. Because you increase or decrease the voltage, we've got to remember that as well, the current going through the transformer is going to be increased or decreased too. If we increase the voltage, we'll decrease the current and vice versa. Anyway, how does it work? Once again, we go back to Faraday's law. And what we need is a conductor or a coil in a changing magnetic field. If we've got a conductor in a changing magnetic field, there's a current induced in it. Correct? All right. So, all we need to do then is create a changing magnetic field. So, I'm going to start with this diagram here. There's two sides to a transformer. On the left of this diagram is what we call the primary coil, or the input. Often in diagrams, the left-hand side is the input. That's just how it works. Okay? What we've got is a bunch of coils of a conductor connected to an AC voltage. Because it's connected to an AC voltage, the current around that solenoid, which is essentially what it is varying sinusoidally. As a result, the magnetic field that it generates is also varying sinusoidally. So if I sketch that magnetic field, at one stage it's going to be like that, and then a split second later it's going to be the reverse, and so on. So we've got a continually changing magnetic field generated here because that's AC current. Okay. If it was DC, it would just set up a magnetic field and remain as is. That's no good for us, as we'll see. Now, back to this diagram. On the right-hand side here is what we call the output or the secondary coil. So, sometimes called the output, often called the secondary coil. Again, it's simply a bunch of coils of a certain number of turns. And if we ignore this green square here, if we just brought the secondary coil closer to the primary coil, the secondary coil would experience a changing magnetic flux and you'd get a current induced in it. You get an EMF across it, so you get a current. But it won't be very efficient. So what we have then is the core. And in this diagram it's shown as green. It's a soft iron core. That soft iron core is going to do this. It essentially concentrates that magnetic field so that that secondary coil experiences a nice, strong magnetic flux. It increases what we call the flux linkage, so that the secondary coil experiences that maximum rate of change of flux. Okay? So again, the whole idea of this soft iron core is to concentrate the magnetic field from that primary coil. Okay? Now, that's the basics of it. What we can do is you'll notice that the primary coil has a certain number of windings, and here the secondary coil's got more windings. If we go back to Faraday's law again, right, EMF is negative N d phi dt, right? Our soft iron core maximizes the flux. N is just the number of loops in the coil. If I increase N, what's going to happen to my output current? It's also going to increase. Sorry, my output voltage, my bad. It's also going to increase. Okay? That's also going to increase. So that moves us on to our first relationship, is that the number of turns and the voltages are proportional to each other. So the voltage generated is basically directly proportional to the number of turns. And that's shown as a ratio. If you want to know what the ratio of the voltages are in the secondary compared to the primary, it's just the same as the number of turns in the secondary compared to the primary. Can you see how they're both secondary over primary and secondary over primary? Okay? So that's our first understanding there. If you want more output voltage, you just have more turns in the secondary coil than the input coil, the primary coil. Okay? So if we look at this one here, okay, if we looked at the second diagram, here's our primary voltage with a certain number of coils, concentrated magnetic flux by our transformer soft iron core. And now though, the secondary winding has fewer coils. So all we know now is that the voltage in the secondary coil is going to be less than the voltage that was across the primary. Okay. All right. Okay. So that relationship we just saw brings us to introduce what are called step down and step up transformers. It's really straightforward. A step up transformer, I'll highlight, yeah, it steps up the voltage. The output voltage is higher than your input. Okay, so if we look on the right hand side here, number of coils, what do you got? In the primary coil you got 1, 2, 3, 4. In your secondary coil, I don't know, double that, which makes sense. 10, yeah. So if we've got, say, 110 volts input, because we've got twice the number of coils here, you got twice the output. 110 up to 220. Okay. A step down transformer just works in the opposite way. A step down transformer, like it says, produces an output voltage lower than your input. So for a step down transformer, you might have 220 input, you'll get 110 output. The little black boxes on your computer charger is a step down transformer. The input is 240 volts. The output is usually about 5 volts. It's USB. Okay, it's usually about 5. Okay. So for a step up transformer, the number of turns in the secondary is greater than the primary, so the voltage in the secondary is greater than the voltage in the primary. For a step down, it's just the other way around. The reverse is true. Okay. Right, let's have a look now, section 9.3, the power output of transformers. A good transformer, like it says, 99% efficient. They're pretty good. How do we make them that efficient? There's two main ways. Okay. First of all, we want to reduce resistive losses. Okay, so the coils are often made of really good conductors like copper, because what that does is reduces the resistance in that I squared R. Okay. As a result, especially at the moment, transformers, they sometimes go missing off work sites and so on because people want to steal the copper in them, which is a shame. Okay. So we use copper. If you really wanted to, you could maybe use gold. Depends on how expensive you want to make your transformers. All right. The next one is the important one for us, is reducing eddy currents. Okay. And like it says, we've seen these before. Eddy currents occur in transformers because the core itself, that soft iron core there, that soft iron core is a conductor. We can't escape that. It's a conductor and it's in a changing magnetic field. So what do we get? We get an EMF and little eddy currents generated. To reduce that, what we do is we get the core and we cut it up into little thin sheets. And we electrically isolate each thin sheet from the next, and it reduces the amount of eddy currents that are generated, and therefore reducing the heat loss. The diagram here shows us, right? Here's a laminated iron core, and what we mean by laminated, of course, is simply breaking it up into, there you go, see these thin sheets here. Okay. If we didn't bother about that, you'd get these massive, great eddy currents if it was a solid core, and you'd get a lot of current. And even though it's made of copper and you've reduced your resistance, the amount of current in the eddy currents is significant, and you lose a lot of energy due to heat. So by laminating that soft iron core, you get little itty bitty eddy currents. And so instead of big I, you get small amount of current and a small resistance as well. Okay. Even though saying that, it's almost impossible to get rid of those eddy currents, and that's why, for example, when we look at these transformers in the substations, this one's from the East Perth Power Station, just across the road. Okay, we get cooling. We've got like a little air conditioning unit there to cool it down, but also this tub here is full of oil, which circulates around the transformer to remove excess heat and keep everything cool. Because a bit like solar panels, the hotter it gets, the less efficient it is. Okay? All right, so we've seen how we minimize that power loss. In most of the examples that we come across, we will assume 100% efficiency, okay? We'll assume 100% efficiency. If I want to make an exam or a test question hard, what we do is we make it like 90% efficient. So the power across the primary, the power across the secondary might be 90% of the power across the primary. So you just got to put a factor in there. Okay? So let's look at our next relationship, which kind of summarizes it, the relationship between voltage, current, and the number of turns, okay? If we say that the power across the primary coil is equal to the power across the secondary, so it's 100% efficient, right? P is equal to I times V, okay? So if we change this around now, what we find, of course, is the voltage is inversely proportional to the current. See how voltage is secondary over primary, current is primary over secondary. So the next relationship, and the sort of summarizes pretty well all we need to know for transformers, is the number of turns is the same as the voltage. The ratio of the turns, is the same as the ratio of the voltages, but it's inverse to the ratio of the currents. So for a step up transformer, you will increase the voltage, but you'll decrease the current. And that's why before we transmit electricity, we have step up transformers. Let's have a look at example 1. We'll do this super quick. Okay. You got primary windings of 200 turns, a current of 5 amps, and an input of 48 volts. The secondary winding is 50 turns. What's your voltage output going to be? Okay, so we start with our basic relationship, and we rearrange this to find that, put simply, your secondary voltage which is what we want, is going to be your voltage of your input times the ratio of the turns. So we had oops, we want not ends, we want the ratio of the number of turns of the secondary to the primary. So 48 volts in, a ratio of 50 turns to 200 gave us an output of 12 volts. So that's probably like a little toy transformer. Okay. If it's 100% efficient, what's the power output? Okay. So your power out is your power in, which is I times V. And the thing we need to remember is that I times V could be for your primary or your secondary. It gives us the current input, and our voltage was 48. 5 times 48 gave us 240, in this case 240 watts. Okay, next screencast we'll continue on with this, guys. Okay.